Most people, particularly people who've elected to study computer science at A-level, will have heard of this guy, Alan Turing, the famous World War II codebreaker, a hero who cracked the Enigma code and saved millions of lives, only to be forcibly chemically castrated by his government for his homosexuality, leading to his suicide. You may have heard of him through the movie The Imitation Game, starring Benedict Cumberbatch. While the movie was undoubtedly entertaining, it's about as accurate a depiction of Alan Turing and his story as The Greatest Showman is of P.T. Barnum. It's a work of fiction. Although it did get two things right: there was a Second World War and Turing's first name was Alan. In reality, Alan Turing was a warm, charming, sociable man who, before his heroics in Bletchley Park, was already a renowned mathematical genius. He's known today as the father of computer science, not because of his code breaking, but because of his work in the 1930s, where he theorised the existence of a single machine which could be configured to solve any problem for which a solution can possibly exist. This theory was his universal machine, now referred to as the universal Turing machine. The universal Turing machine is not a real physical machine, it's a theoretical device that followed simple rules which Turing believed, correctly as it turned out, could be used to solve any solvable problem. The universal machine was not, despite what The Imitation Game will tell you, a mechanical AI simulation of his dead boyfriend Christopher. Seriously, that movie. In this lesson, we're going to look at the Turing machine and ultimately the universal Turing machine. We will learn how it operates and understand its impact on computer science. For this lesson, you will need access to the internet, preferably on a computer, as you will be using an online Turing machine simulator. So what is a Turing machine? A Turing machine is not a real machine. It's an abstract mathematical model of computation. It was devised by Alan Turing in 1936 and used to prove that some problems are unsolvable. It can be shown that if a problem cannot be solved by a Turing machine, then it cannot be solved by any mechanism. Let's have a look at his proposed concept. A Turing machine consists of a finite set of states, a finite alphabet of symbols, an infinite tape with marked off squares, a sensing read and write head that can travel along the tape one square at a time, and rules for transitioning between states and reading and writing and moving along the tape. On each cycle, the Turing machine does the following. It reads the value of the current square and it reads the current state. Then, based on the value and state, it writes a value to the current square, changes the state and moves the tape left or right. The rules governing how the machine behaves can be expressed with transition functions, which look like this. This particular transition function tells the machine that if the current machine is in state S2 and the current character on the tape is 0, then change the state to S0, write the character 1 to the tape, and then move the reader one space to the right. This is an example of a Turing machine that performs a specific role. Let's investigate what it does using an online Turing machine simulator. The website we're going to use is turingmachinesimulator.com. It's about as easy a website to find as you're going to get. So once you've got there, you'll be presented with a Turing machine simulator like this window here. If you look at the syntax that's given in there, it tells you some things to fill in. Anything starting with / is a comment. You don't particularly need those, so I'm going to get rid of them. We're given the option to provide the name of our Turing machine. I'm not going to bother with that one. You can give it a name if you want to. And then init here is for the initial state. It says down here our start state is S0, so let's put S0 as our start state. Then our accept state is which state we intend to finish in. Again, it's not a requirement, but in this case we're going to finish when we get to S2. So I'm going to put that as S2. And then it tells you how to put in your delta functions, your transition functions. You have to put on the first line, the left-hand side, the state it's looking for and the value on the tile that it's looking for. Then underneath, you put the new state, the symbol that'll be written, and then the direction to move as a triangle bracket. So, I'm going to get rid of all of this and start putting in this program. This first one here says if it's in state 0 and it's reading a 0, then go to state 0, remain in state 0, write a 0 on the tile, so nothing changes, and move to the right. There's our first transition function. The next one here is if we're in state 0 and we find a 1 under the reader, then stay in state 0, write a 1, move to the right. This one here is just that one, and this one here is that one. And if I continue and put the rest of them in, and there we are. I've transferred all these transition functions to here. We then click compile, and it's now created our Turing machine using that transition function. We then have a choice of inputs, and for this one it's all about ones and zeros. So I'll put in a random string of ones and zeros, press load, and now it's ready to go. And you can run through. I'm going to slow it down so we can see what happens. I click play, and it says we're in state 0, and we're reading the 1. We're staying in state 0, and it's using these transition functions to do what it needs to. Eventually it'll reach the blank space. State 0 and blank should change to state 1. Let's see if it does. And it does. And it tells it to move that way. So now it's in state 1, it's doing different things when it encounters each of the tiles. Eventually it will get to the blank tile in state 1, it'll change to state 2, and that's the end of it. So that there was a Turing machine to invert a string of bits. Every 1 was changed to a 0, and every 0 was changed to a 1. Now here's a task for you to try. Using the simulator, create a Turing machine which has an alphabet of A, B, C. That means the tape consists of A's, B's and C's only. The machine must move the head all the way to the right of the string until it reaches the end. Then step back through the string, replacing every A with a C and every C with an A, but leaving B unchanged. If you succeed with this, you can try the advanced task, create a Turing machine that takes a binary number and adds 1 to it. Pause the video here and have a go at these tasks. We'll go through these in the live segment. Alan Turing took this model one step further with the universal Turing machine. He demonstrated that a Turing machine could be built where both the input and the transition functions are contained on the tape. In other words, he proved that a programmable computer is possible. A single machine could be built that could be programmed to perform whatever function we give it. He proved this nearly a decade before the world's first programmable computer, Colossus, was created by Tommy Flowers. Ultimately, Alan Turing is the father of computer science because he proved what we now know as a computer was possible years before one was ever built. As well as saving millions of lives during the war, he began the computing revolution, which led humanity to where it is today. Computers as we know them and computer science wouldn't exist without him. I'll see you all in September, and we'll explore much more of what he made possible.